Hey folks, hey, thanks for joining me here today. I'm sure you're well aware, and we've heard it for years really, that the worldwide data footprint is growing. I think about it a few years back. I remember thinking about that thumb drive, that coveted giveaway at conferences and such. And folks started talking about zettabytes of data, literally billions of those thumb drives worth of data being generated every year. And I couldn't really wrap my head around it. How could we store all of that data, and how expensive would it be to do so? And perhaps most importantly, what are we going to do with it all anyway? How can we access it? How can we search it and derive insights from it all? Well, first of all, my eyes grew wide when I saw the sheer size of IDC's predicted data sphere, what they call the global amount of data that's created and replicated every year. Well, last year we came in at just over 64 zettabytes with a 23% compound annual growth rate for the next 5 years. But it came as some comfort to find out that a lot of that data is ephemeral. In other words, it's used by an application and then it's discarded. So only 6.7 zettabytes is actually stored for what IDC calls the global storage sphere. Yeah, okay. Did I say only? That's really massive. And although it's not quite growing at the same rate as the data sphere, it's pretty darn close at 19% CAGR. Now, really to put this in perspective, imagine all the data we've amassed since computers have been around. Over the next 5 years, we'll more than double that. IDC Research Vice President John Riding recommends that organizations should prepare to store more data along with their digital transformation initiatives so they can accelerate their data analytics, driving business insights. Now, I'll contend that one of the best ways to do that is by embracing object storage. But first, it might be prudent for me to talk a little bit about the different storage protocols, and that's, file, block, and object, and where each one fits. I'm not really advocating that everything move to object, but embracing object storage will help manage this onslaught of data and make it useful for data analytics, business intelligence, and emerging workloads like artificial intelligence and machine learning that we've all been hearing a lot about lately, right? So first, there's file storage. And I think most people are familiar with this. If you think about your first interactions with a PC, for example, that used a file system protocol, it's hierarchical, similar to a file cabinet. I remember back in the 90s, I had a manager with a couple of file cabinets in his cube, and one of the drawers was labeled maps, and then within that drawer there were folders in the drawer, A through D, E through H, so on and so on. And then in the folders there were actual roadmaps for states and cities, and he grabbed one of those as he rushed out to the airport. I mean, man, I was really glad when MapQuest came about. But anyway, I digress. That's the same hierarchical idea behind a file system. Files are stored in folders within a directory, and then they're accessed via different file system protocols, typically SMB if you're running on a Windows machine, or NFS, Network File System, for Unix or Linux environments. And they're typically written and subsequently accessed as a whole on a disk partition. Now, typically, if you want to share a file and collaborate with somebody, you can share your drive via the network or through a network area storage or NAS device. These were deployed to let many people share a repository of files within a team. Well, now the nice thing about file storage is that it typically has high throughput at a reasonable cost, and you can tier different data across different types of media for better performance. So, you could have cold data sitting on spinning devices, you could have hot data sitting on flash or NVMe devices. It's also inherently POSIX compliant, and many applications are already written expecting file protocol for access, so it's pretty ubiquitous. Now, from these standpoints, file is a simple choice, but it can be difficult to scale, not only capacity, but accessibility. Think about it this way. When you want to access the file, your machine has to go and find and load that file into memory. And it has to do so for the complete file. Now, that's typically not a problem if you're working on your computer, but imagine if the file is very large and suddenly a lot of people are trying to get to it at the same time. It can bring up network issues. It can bring up bottlenecks in your network. Now, there are some software-defined storage solutions that have workarounds, like Lazy IO, for example, in Red Hat Ceph Storage to help with this issue. But still, file systems don't scale very well, and it becomes difficult to manage as it gets larger. Also, the metadata. That's the data about the data, like when the file was created, where it lives in the directory, the size, all of that type of information. that metadata is very limited in a file system. This makes it a lot harder to search. And, sure, you could put more information into the file name, but then that becomes long and cumbersome. So how do you divide up and adaptively balance that metadata? This ushers in most of the complexity, both in system implementation and in workarounds. Now, suffice it to say, file storage does have its place. It's great if you have smaller teams who need to collaborate and share a number of files. But I'm sorry to say it's not going to get us to solve our data growth issues that we mentioned before. So let's consider the next thing. Let's consider block storage. This is a much more efficient way to store and retrieve data. Essentially, your application takes all of your data and cuts it up into chunks of uniform size, typically 4K or 8K blocks, and then distributes those chunks across volumes. Now, another great attribute is that your application can include resiliency features in the way that it writes the chunks across volumes. Now, while in file storage you had limited fixed metadata, actually with block storage you don't really have metadata at all. Instead, everything is mapped by file location and it's stored in an index somewhere on file, on a database, etc. And when it comes time to retrieve that data, the application looks for the map of where the chunks are located and then pulls them back together so you can see that file. Now, typically block storage is stored on a storage area network or array. That's normally what we see out in data centers, and those are directly connected to the servers running the application via a fiber channel or an iSCSI interface. And there's typically two or more controllers in an array that handle the writes and reads across volumes that are created across actual physical media, physical disk. Now, the great thing with block storage is that it's very fast with high inputs and outputs per second, or IOPS, and low latency, meaning that your application response times will be much faster. Now, block systems can also be accelerated by implementing all-flash devices, which, of course, are much more expensive than spinning disk. But since a lot of the data stored in block devices are prone to inefficiencies, making use of compression and deduplication topologies can sometimes greatly reduce the usable disk space, and thus you optimize your raw capacity. Now, all that said, block storage is very expensive in general, and it doesn't scale much more than a petabyte within an array or a SAN, etc. Likewise, the data is typically held close to the application, and that implies complexity as you plan for your business continuity scenarios. And still, it's great for structured data. Typically if you're looking at databases, especially transactional applications that store a lot of data in a relational database, think of your human resource management type applications, financial applications, AR, AP, stuff like that. It's also good for virtual machine environments. All right, so now we're going to talk a little bit more about object storage. Now, this is very different because it stores everything in a flat namespace. The data is chunked up, somewhat similar to blocks, but instead of being distributed across volumes, it's written in objects to the same object bucket. Now, the objects are made up of the data itself, along with metadata and a unique identification key. Now, the great thing is that this metadata is highly customizable, not like file storage where you can only have a set of static type metadata, or you could rewrite your application to customize it. With object, the metadata is inherently very customizable with tags, so that when someone wants to search for the object, they can do so either by knowing the key or by searching on something that might be stored in the metadata. Typical protocols for object storage are Swift for OpenStack private cloud environments, or especially the S3 protocol originated by AWS, which has pretty much become a de facto standard for cloud object storage. Now, depending on the architecture of the object storage software, you can typically accelerate performance by attributing a small amount of the expensive all-flash devices, NVMe devices, etc., for the metadata cache, while optimizing costs with hard drives supporting the overall data layer. This also allows you to increase usable capacity, having an option for erasure coding data resiliency versus pure replication, depending on your workload. Now, finally, object stores are typically built on a distributed scale-out architecture that continues to add capacity at near linear performance virtually indefinitely. This means really that object storage is massively scalable. It easily handles tens or even hundreds of petabytes per cluster. Enhanced access controls and policy features provide secure access for multi-tenants, and it can handle access by many devices all at the same time, as well as massive parallel ingest, which makes it perfect for cloud storage. Now, I mentioned a distributed scale-out deployment, but this also means that you can perform rolling hardware upgrades while your data is live. Now, object storage is also characterized by high throughput, and importantly, as we're dealing with massive data growth, object storage really has the lowest cost per gigabyte available. Now, object storage does tend to have a slightly higher latency, but you can tune your environment and follow some architectural best practices to mitigate some of that. And a lot of the traditional applications weren't written for object, but as you're planning your digital transformation, you should focus on modern cloud native applications that take advantage of object stores, and older applications can be revamped or replaced over time. So overall, as you can see here, object storage is great for large amounts of unstructured data and cloud native applications. It also makes a great place to store media, backup targets, archives, as well as creating a data lake for large scale analytics and some of these new things around artificial intelligence and machine learning modeling type workloads. Okay, so why is all of this important? Well, according to a survey by 451 Research, more than half of respondents said that most or all of their application development is now cloud native. I've included a number of additional workload proof points, things from Crunchy Data Postgres to IBM DB2 Data Warehouse, Starburst Trino, Jenkins. Adieu. Thank you so much for joining me today and enjoy the rest of the conference.